Hi everyone, these are your 2.1b notes describing the location of an individual within a distribution. Last time we talked about how there are two main ways to do that, either by calculating the percentile that that individual is at, or by calculating that individual's standardized z-test score. Today we're going to talk about the final learning target in this section, which is to describe what effect either adding, subtracting, multiplying, or dividing by a constant throughout our entire data set would have on both the shape of the data as well as the center and spread of the data. Make sure you label your notes 2.1b and then move on to the first example. So let's take a look at one scenario. You don't need to write anything down on this page because we're going to look at it more in depth next, but I just want you to think back to the Chapter 1 test scores that you got last week. What would happen if I were to add 5 points to everyone's Chapter 1 test scores? Most of you would love that, right? So someone who got a 30 out of 50 would now earn a 35 out of 50. How would adding 5 to the whole class's test scores impact the average, the mean? How would it impact the spread, the standard deviation? Then think about a second scenario. Instead of adding 5, what if I multiplied everyone's test score by 2 so I could put them in the gradebook out of 100? Now someone who got a 30 out of 50 on the test actually gets a 60. How would that impact the mean or the standard deviation? Let's take a look when we have some data to compare this. So below you can see dot plots and numerical summary statistics from original test scores and then test scores that have been adjusted by adding 5 points. So how did this change things? Well, first off, if I look at my original dot plot compared to my adjusted dot plot, there does not seem to be much of a difference in the overall shape of the dot plot. The original seems pretty skewed to the left by a couple of these outliers, down at maybe 12 for the minimum, and maybe even this one at about 18. The adjusted scores, when we added 5, now this 12 just becomes an outlier here at 17, and there seems to be one at about 23. So the adjusted scores are also skewed left. So the overall shape does not seem to have changed very much. Let's take a look at how the measures of center change. Take a look first at the means. I notice the mean of the original data is at 35.4. About right here, which makes sense. It's just below this peak since it's being pulled down by the low-end outliers. The mean of the adjusted data is 40.44, 5 points higher. About right here. Still just to the left of that main peak because it's being pulled down lower by the left data. So notice the mean went up by 5 when I added 5 to each test score. The same thing is true for the median, the midpoint. The median of this data is here at 38, near the main peak. In the adjusted data, the median goes up by 5 points again, from 38 up to 43, which I can see in the second adjusted dot plot. That's also going to be true for any individual values. So for example, the minimum and the maximum as well as the quartiles all also went up by 5 points. So in general, what we should be observing here is that when I increased each data value by 5, the mean, the median, and all of the individual points themselves also increased by 5. So what I would write down for this example, example number 1, is that when I added 5 to each test score, the measures of center also added 5. They went from 35 to 40, or the median went from 38 to 43. And I can see that shift visually on my dot plots where the mean and median look like they're in one spot in the original and then shift upwards by approximately 5 in the adjusted. Now let's take a look at the measures of spread. So when we're looking at spread, we're not looking at where the data points are, but instead looking at, for example, the difference between the highest and lowest data point. I'm going to move my video out of the way so that you're able to see the range and IQR on the end there. Notice the range stayed the same. So when every point shifted up by 5, the difference between the highest and lowest point didn't change. Same thing with the IQR, the difference between Q1 and Q3 didn't change when every point increased by 5. And the same is true for the standard deviation. So what I want you to write down for those is that the measures of variability or the measures of spread stayed the same. Specifically, we pointed out the standard deviation, IQR, and range. So for example 1, in the first scenario where we added 5 points to everyone's test score, the measures of center also added 5, mean and median, but all the measures of spread stayed the exact same. Let's take a look at the second scenario. So in the second scenario, I multiplied everyone's test scores by 2. Let's look what happened. Now we have our original data clustered down below because remember they were out of 50. Now look what happened when I doubled people's test scores. So someone who got 40 now gets 80. Notice they got a lot more spread out, right? So in this data, we're noticing maybe a difference in both the center as well as the measures of spread. This is verified when we look at the numbers. So when we look at the numbers for mean and median, we're seeing the exact same thing that we saw before, that the measures of center all change by whatever change I made. So I multiplied by 2, the measures of center also multiplied by 2. They went from 40 to 80 for the mean, from 43 to 86 for the median. But the difference is when I was multiplying by a number instead of adding, the measures of standard deviation, IQR, and range, the measures of spread, those measures also doubled. And that's the main difference between when I add versus when I subtract. Or excuse me, when I add versus when I multiply. Multiplication changed both things. All the measures of center and all the measures of spread multiplied by 2. When I added, all that changed were the measures of center. So go ahead and write that down for the 2 scenarios. So in the first scenario, when I added, only the measures of center changed by whatever I added, versus when I multiplied, everything changed. Here's a synopsis of that for your notes. So if you didn't get it from the example, here's a time when you can summarize for your notes. When I added, or the same thing would have happened if I subtracted, although don't worry, I'm never going to subtract 5 points from all of your test scores. But the same thing happens when I add or subtract. The measures of center and the individual data values themselves will all add or subtract by that constant. However, the measures of spread as well as the general shape of the distribution will stay the same. When I multiplied, or the same thing would have happened if I divided by a constant, when I multiply or divide, both things changed. Both the center or individual data values multiplied by that constant, as well as the measures of spread also multiplied by that constant. However, in both situations, the shape of the distribution, whether it's symmetrical or skewed, will stay the same. So in summary of example 1, adding changes measures of center, multiplying changes both measures of center and measures of spread. Make sure you have everything on this slide written down for certain before moving on, because this is really the main idea from today. So we're going to finish by looking at just 2 final examples. The first is about a long jump. So a member of the track team is practicing the long jump and records the distances in centimeters of the jumps. Some numerical summaries of the data are also included below the dot plot. After talking with his teammate, the jumper realized that he measured his jumps from the back of the board instead of the front, so he had to subtract 20 centimeters from each of his jumps to get the correct measurement. So the first thing I want you to notice is that in order to get the correct measurements, he needs to subtract from each of his scores. So notice we're going to be in the first scenario, adding or subtracting. Remember, adding or subtracting only changed the measures of center, not the measures of spread. So the first question is, what shape would the distribution of corrected long jump distance have? Next, calculate the mean and median of the new long jump distance after subtracting 20. Then calculate the new standard deviation and IQR of the corrected long jump after subtracting 20. So go ahead and do A, B, and C before moving on to the next slide where I'll go over the answers. I'm going to move my video so that you can pause on this slide to answer A, B, and C. So make sure you have an answer for A, B, and C. You'll probably want to pause the video because you'll need those summary statistics as well as to look at the shape of the graph to come up with answers before moving on to the next slide. Once you're satisfied with your own answers for A, B, and C, you can move on to the next slide where we'll go over them. So let's take a look at what you came up with. For the general shape of the distribution, remember the shape of the distribution stays the same regardless of whether I add, subtract, multiply, or divide the data by any consistent value. So I would say that my original shape, I'm going to draw a line over it so that we can see the shape a little bit more clearly. I would say that the shape here is pretty symmetrical. Maybe there's a little bit of a lower point on the left, but there's just as much data over on the right. So I would say that this data set is roughly unimodal and symmetric. There aren't any obvious tails or outliers. That means that the corrected long jump just shifted down by 20 would have the exact same shape. So the shape will stay as the original, roughly symmetric and unimodal. Now let's take a look at the mean and the median. So to do that, I'm going to look at my original mean and median. My original mean was at 577.3 centimeters, and my original median was at 577. I know from the notes that we took in the first example that measures of center, including mean and median, will add or subtract by that constant value. So to find the new mean and the new median, I just need to subtract 20 from each of them, since it said that's how much distance he needed to subtract from each value. So 577 minus 20 would give me 557.3, and then for the median, 557 minus 20, oops, excuse me, that was an error, 577 minus 20 would give me 557. I'm going to correct that value so that you have the right answer right there. So this should have said 577, since that's our median right there. Minus 20 will give me a new median of 557. Now we're going to do the exact same thing for the standard deviation and for the IQR. I'm going to move this so that you can see both of the quartiles. So let's take a look. So this original standard deviation was 4.73. So on average, we could say that his jumps were 4.7 centimeters from the mean. We didn't have a calculated IQR, but we could have calculated it simply by subtracting Q3 minus Q1. For our new standard deviation and IQR, because this is a subtraction problem, and we know that works the exact same as an adding problem, and adding or subtracting do not change measures of variability or measures of spread. So my standard deviation and IQR will stay the same. My standard deviation stays 4.713. My IQR stays the same number I get when I do Q3 minus Q1, which is 7. So because this was a subtracting problem, which works the same as adding, my measures of center all subtracted by 20, while my measures of spread stayed the same. Let's take a look at one final example. Let's take a look at cabin temperatures. So here's our setup. During the winter months, the temperatures at the Starnes' Colorado cabin can stay well below freezing, which is 32 degrees Fahrenheit or 0 degrees Celsius, for weeks at a time. To prevent the pipes from freezing, Mrs. Starnes sets the temperature of the thermostat at 50 degrees Fahrenheit. She also buys a digital thermometer that records the indoor temp each night. Unfortunately, the thermometer is programmed to measure the temperature in Celsius. So what's below is a dot plot and numerical summaries of her thermometer's reading every night at midnight, but in Celsius. She wants to be able to compare that to the thermostat, which is set in Fahrenheit. So using the data in Celsius, I want you to find the mean temperature in Fahrenheit, and then I want you to calculate the standard deviation in Fahrenheit. To do this, you're going to use our equation that converts between Fahrenheit to Celsius. Some of you may have seen this equation before in a previous math or science class. So we'll be using this equation that converts from Fahrenheit to Celsius. One important thing to notice about this equation is that it involves both addition of 32 and multiplication by 9/5. So let's take a look at how we would do this. So for mean and standard deviation, we're going to have to take into account when does it matter that I'm adding and when does it matter that I'm multiplying. So first, finding the mean temperature. Well, I can see that the average temperature in Celsius was 8.43. And I know that mean temperature is impacted both by adding and by subtracting. So because mean is impacted both by adding and subtracting, I'm going to use the full equation. I'm going to take 9/5 times my mean in Celsius, so 9/5 multiplied by 8.43, and I'm going to add 32. So the reason why I'm going to do both the addition and the multiplication is because I know measures of center are impacted by both things. Measures of center change when we add and when we multiply. So here's my completed answer. You can see I plug in the mean for my degrees Celsius, and I do the equation 9/5 times 8.43 plus 32. That gives me 47 degrees. So that means that on average, Mrs. Starnes' thermometer is telling her that inside her cabin it's 47 degrees at night. Since the question asks us if the thermostat setting seems accurate, we're going to say probably not, because she was setting the thermostat at 50 degrees and her thermometer is telling her that on average it's closer to 47. So it seems that the thermostat is a little bit off. Next, let's go and calculate the standard deviation. So notice that the standard deviation in Celsius is given to us in our summary statistics as 2.27. Now, when I go to use this equation, I know that measures of spread only change when I multiply. Measures of spread do not change when I add. So instead of using this entire equation, I'm only going to use the part of the equation that multiplies, which is the 9/5 C. So let's take a look at my answer. So I'm going to take my standard deviation in Celsius, 2.27, and I'm going to multiply by 9/5 because multiplication does change our standard deviation. When I take 2.27 times 9/5, I get 4.09 degrees. And again, that was because multiplying by a constant only impacts standard deviation, but standard deviation was not changed by adding. What this tells us is that on average, every night in her cabin differs from the mean by about 4 degrees on average, which is pretty significant. If each night in your house or your cabin or wherever you are at the moment is 4 degrees different, sometimes 4 degrees can feel pretty significant. This is the end of your 2.1b notes. Remember, our main learning target for today was that when we add or subtract by a constant in a set of data, The measures of center will all change by that addition or subtraction, while the measures of spread will stay the exact same. When we multiply or divide by a constant, everything will change, both the measures of center and the measures of spread.